Okay, so now we have the last talk of this day. The speaker is Noé Bárcenas. He is from CCM, Centro de Ciencias Matemáticas, in the city of Morelia, UNAM. And he will talk about Stolz Positive scalar curvature, surgery, exact sequence, and loading of nature homology. So you have 40 minutes, Noé, and thank you very much.
Well, thank you very much for the invitation. And I apologize for the extremely long title. I only realized afterwards that it is the most clear example of a technical title. No? So you begin with Stolz positive scalar curvature, surgery exact sequence, and even low dimensional group homology. And well, this is a work. It has already been finished, done in collaboration with Rudolf Zeidler in the University of Münster currently. So this is located in the area of the topology of scalar curvature, but it has some connections to finite groups. There are going to be some finite groups over there, and a group homology. So that's the idea. And of course, Bordesman surgery. This is very important in this work. So let me please just define a little bit of what is the problem about. So scalar curvature, this is a real valued function defined over a manifold. And the idea behind it is that scalar curvature compares the volume of n-dimensional balls in the Euclidean space with Riemannian balls on M. And precisely, if you take the volume of a Riemannian ball at some point on the manifold, and the Euclidean volume of a ball, which is meant to parameterize a chart of the manifold, you get this expansion where the term of order 2 is this function, which is called the scalar curvature, divided by some dimension normalization factor here, and then terms of higher order. So this is a function on the manifold, and if a manifold has a positive scalar curvature on every point, and this is what we are going to abbreviate as PSC, or having a PSC of positive scalar curvature metric, then the volumes of Riemannian balls grows lower than the volumes of balls in an Euclidean space. Examples that we could consider: spheres with the usual metric, quotients of these spheres via orientation preserving group actions like real, projective, or inverting in the case of real, projective or quaternionic projective spaces are some examples of manifolds which have a positive scalar curvature metric inherited from a PSC metric on the original manifold. So products of these manifolds with another manifold can be arranged to have a metric which is of positive curvature, and from there you can consider the total spaces of smooth bundles which have a manifold with a positive scalar curvature metric. So these are examples of such manifolds. And the most interesting question about positive scalar curvature is that there are topological obstructions for a manifold to admit such a metric. And this is a big story. It's basically about index theory and how Dirac operators play a role in the topology obstructions behind the fact that a manifold could accept a metric of positive scalar curvature. And I will try to outline some of the aspects of this story. And if you consider smooth spin manifolds, and you make the choice of a spin connection, then you can define a Dirac operator. This is the Atiyah-Singer operator. And then you can consider the action of this Dirac operator on the sections of a spin or vector bundle over M. And then here is the crucial fact, the so-called Bochner-Lichnerovich and Schrödinger formula. If you compose this Dirac operator with itself, you will obtain the connection Laplacian and then the scalar curvature as a function. No? So this is acting as scalar multiplication over the sections, on the sections of the spin or vector bundle. And if the scalar curvature is always positive on every point, then this expression tells you that d square, the square of the Dirac operator, is an invertible operator. And then there are properties of the Dirac operator, namely ellipticity and the fact that it acts grading and essentially Cephal-joined with respect to that grading. These conditions all imply that the kernel of D, and which is equal to the kernel of the D square, is of finite dimension. And moreover, that this difference of the dimension of the kernel and the co-kernel is equals to 0. So here you see everything could be phrased in terms of analysis, since the Dirac operator is an analytical gadget. But then there is the surprise, the Atiyah-Singer index theorem, which tells you there are actually topological obstructions for this analytical relation to hold. And this is the result by Atiyah and Singer, the homological formula for a closed smooth spin manifold. There exists a polynomial in rational Pontryagin classes, the Eje genus, which when you evaluate it on the fundamental class on the manifold, you obtain exactly the difference of kernel and co-kernel of the Dirac operator. So if we go back just one slide, we have the this analytical quantity, the difference between the dimension of kernel and co-kernel, and then we have a polynomial in rational Pontryagin classes. So this is an indication that topology, and more specifically Bordism, should play a role. So the index of the Dirac operator is invariant under spin cobordism. In fact, if you consider the Pontryagin classes, so the Pontryagin numbers are invariant of rational oriented Bordism. So you don't see directly from this formula that this is an invariant of spin Bordism, but actually more from inherent structural properties of spin Bordism. So but at least you could see that it is an invariant under Bordism, and the question of how spin Bordism plays a role in this is really at the point. Yes, sure. Anyone? Okay. So here is the connection. If you, there's a theorem of Gromov, Lawson, and Schoen and Yao. If you have a simply connected manifold which has positive scalar curvature, and then if you obtain a manifold through surgery of codimension at least 3, then this manifold carries a metric of positive scalar curvature. So in the simple connected case, if you have enough space to do surgery of this codimension at least 3, then you can construct a metric of positive scalar curvature. Um, so in this case, in the simply connected case and in the high dimension, so in order to do a surgery of codimension greater than or equal than 3, you need at least 5. So the question whether a manifold admits a metric of positive scalar curvature, it is completely a matter of spin Bordism over there. So you could replace through spin surgery or spin Bordism there, and the question remains valid for the original manifold or the manifold after surgery, and it's completely equivalent. Um, so this motivated the following circle of ideas, which led to the definition of a kind of surgery exact sequence for positive scalar curvature. So recall that you can define a Bordism with any structure on the normal bundle. So you can take spin Bordism, and if you take CW complex, you could define this homology theory where cycles are uh, spin manifolds of a certain dimension. We have this kind of singular cycles which go from the manifold to the CW complex, and then we put on these manifolds on these cycles, which consist of a manifold and a map to X, the relation generated by spin Bordism. So now what we want to do is to try to consider the part of Bordism which is of positive scalar curvature, right? And the warning is that this is not going to be a homology theory, but you can still consider this. It will give you groups which are given by generators consisting of a spin manifold of a certain dimension, and we put the condition that you have a metric of positive scalar curvature on the manifold, and then we put a spin Bordism of where the manifold which gives the Bordism gives the positive scalar curvature Bordism. And then this is not a homology theory, as I told you. So excision fails. So if you try to adapt the Morse function argument, which you usually consider for trying to prove that Bordism is a homology theory, then you need surgery in order to proceed on this, and in order to produce the needed surgeries over there, you need this high codimension to apply the Gromov Lawson or Jaushon theorem on this surgery, and this is the reason why these groups are not homology theory. So excision fails there, but still we can put these groups, which are an interesting invariant for a manifold, if it accepts a metric of positive scalar curvature. You could begin to wonder, well, this is kind of Bordism of structures there. So I could consider this invariant and try to say something more about the metric of PSC that you can consider on a manifold. So now I'm almost all the way through the definition of the Stolz surgery exact sequence, and now I will define these R groups. Now the dimension is going one higher, and it consists of triples where I have a compact manifold with boundary now. Now I assume that this is a spin manifold. I have a metric on the set of positive scalar curvature on the boundary, and I have a continuous function from this spin manifold. And now the equivalence relation is a bit more complicated. So now we consider Bordism, but this Bordism has an assumption about the metric. So the idea is that it has a product metric near to the boundary. So you have a collar, and over there you put a PSC metric on this collar, and otherwise you let on the interior go as it wants. But we have this PSC metric on a collar neighborhood of the boundary. And the reason why I defined the R spin groups this way is that they obviously come with a boundary map to the positive scalar Bordism to the right, in one dimension less. So here you can see from Rn, I have a map to the positive scalar curvature Bordism on the right hand side, and then I have the spin Bordism in this depiction in the middle. So this is an analogy to the surgery exact sequence. So Pn, this group of positive scalar curvature Bordism, they're sort of a very of a kind of structure set. Then we have a homology theory over there, which is the homology theory given by spin Bordism. And then on the right-hand side, we have what plays the role of the normal invariance in the surgery exact sequence. And again, so the homology theory is omega n spin, and this is supposed to be the easy part. This is the part for which you can use all kinds of local to global principles like spectral sequences to compute. And what you are actually interested is Pn as a kind of a structure set and Rn as normal invariance. And the goal is that we are going to give some bounds about the rank of these groups, but after a couple of elaborations. So are there questions at this point?
Sorry, no, what is the middle map?
The middle map, this is the map which, do you say from spin Bordism to R spin?
Yes.
So I have, oh, let me see. This is probably, oh, let me see. So this, since I have no boundary here, that's the point. I could just push it over there. So that's the map. Yes. So implicitly, I have no boundary in the right on the left hand side. So I just consider it as a part in Rn. But still, this sequence is exact, and well, the crucial difference also to surgery theory is that here things things are groups in this surgery exact sequence, right? So okay, so just a small comment. So Rn, the normal, which plays the role of the normal invariance, you can use a PSC surgery argument. This is called just applying the Lawson Yao and or Gromov-Schoen theorem. It only depends on the fundamental group. So, and this is also a parallel to the classical story. So now there is a whole series of works and conferences and methods which go by the name mapping surgery to analysis. The idea is that the surgery exact sequence has several kinds of invariants which take places to in versions of K homology, and well, the four goals of this method go back to Hickson and Rowe. You could find it in three papers of these people, Hickson and Rowe, in the 90s in K theory. But also Mishenko, he even did a very interesting a mixture of analytic and algebraic surgery theory. So perhaps that's an example of when Professor Landweber was telling us that communication between East and West was not very fluid. So there's lots of elaborations of Mishenko in the 60s or 70s about these kind of ideas, which just become concrete in the 90s and 2000. And probably more specific what we are doing in the topology of scalar curvature, I should mention the names of Paulo Piaccia and Thomas Schick. And this mapping surgery to analysis takes the following form. We consider the PSC surgery exact sequence on the top, and we plug in X equal the classifying space of a discrete group. So we have a omega spin, R spin, Pn spin, and they repeat. And now there are invariants. Please concentrate in the middle invariants. I'm gonna telling you something about the others later. So the lower row, this is the map given by the coarse bound cone assembly map. So you see on the left hand side you have KU. This is a notation for a topological complex K homology of the classified space. On the right hand side you have the K theory of the complex C-star algebra associated to the discrete group gamma. And then from Rn, you have an index theory for manifolds with boundary coming down, which was the beginning of the ideas by Hickson and Rowe. So the challenge in that kind of papers was doing index theory for some very specific kind of manifolds with boundary, and then this is the index map over there. On the right hand side, you have the so-called analytical structure set. This has a definition completely in terms of operator theory. So this is the complex K theory. That's also notation for K theory of a certain C-star algebra. And this is the C-star algebra of pseudo-local finite propagation operators on the universal cover of the classifying space. So this is just the Hickson and Rowe setting for the algebras of pseudo-local and finite propagation operators and the relative K theory groups, and this is just a name for the group in the middle. So this is the analytic surgery structure set. And then, as I told you, the index maps for manifolds with boundary. This is the left-hand side. And then rho is the higher rho invariant. So there are four goals of the rho invariant appearing in the first equivariant versions of the Atiyah-Singer index theorem. And this is a generalization of that. So if you take a manifold, you take the homology in the middle dimension, it has an intersection form, and then you can define a kind of rho invariant in this situation, and this is this map over there. And I will tell you in a few slides something about the exterior columns and how they're interacting. Okay, so now There is a more refined version. If you see this, this is complex, the complex K theory on the bottom of the diagram. Rudolf Seidler and William Yu and his student Xie consider this finer replacement for the mapping surgery to analysis program. So this is in KO theory, in real K theory, and why it is a refinement. As you may have known, spin Bordism is completely determined by KO theoretical Pontryagin classes. No? Complex K theory detects a bit of this structure, but KO is more refined, and you have a very analogous situation. You have an index theory for manifolds with boundary as the crucial part. Then you have the raw invariants coming from the groups Pn into a structure set which is defined completely analogously. And then with Nu, I designed what is, I will call what is called the Novikov assembly map. So this is kind of of a of an assembly map for KO theory over there, completely analogous to the complex Baumkon assembly map. So the goal now is to give bounds of Rn and Pn by using the KO theory of classifying spaces over there, and some positive knowledge about the Novikov assembly map, which boils down to positive knowledge about the Baumkon's assembly map. And for this, what we are going to do is to rationalize everything. And this goes under the name for complex K theory of the Chern character. We are going to do a real version of it, so we adopt the name of Pontryagin Chern character, let's say. And in fact, we are going to use very specific tricks of understanding this Chern character in low dimension, which go back to Michel Mattei. If you consider a discrete group, I can construct the set of elements of finite order, and I will consider by the moment just the elements, because I want to have the action of conjugation over here. Later we are going to have conjugacy classes, but now just imagine that this is something on which gamma obviously acts by conjugation. I can consider the complex vector space of functions defined on these sets of elements of finite order with finite support. And I will put this Q over there, FQ, to denote the set of such functions which have this property that if you apply it to the inverse of an element, you get -1 to the Q, and also with the finite support condition over there. What is this for? This is a generalization of so-called real conjugacy classes, which play a role, for instance, in the real representation K theory. If you put Q equals 1, this is the definition of a class function defined on real conjugacy classes. But since we are dealing with implicitly with equivariant KO theory over here, we also have to keep track of possibly quaternionic or whatever conjugacy classes, and this is a way of concentrating in the aspects of the conjugacy classes that we need. Okay, so Now let me quote the result I'm going to use. So there is this theorem by Michel Mattei, which tells you that the so-called delocalized Chern character is a homomorphism from the left-hand side. This is K-homology, equivariant K-homology of the classifying space for proper actions. This is what appears in the left-hand side of the BAM-CON map. Um, into this group homology with strange coefficients over there. And for complex K theory, I don't need this trick of the FQ. I'm going to use it for real K theory, but it tells you that if you're interested in K naught, in K homology, and K1, then there exists this isomorphism to this strange group homology with the specific coefficients on these modules over there. And the crucial part by Mattei is that he gives some inverses by actually noticing that homology classes in degree 0, 1, and 2 can be represented by manifolds, actually by surface groups and whatever. So he produces explicit inverses for these maps, and we're going to use these inverses in a crucial way. They go into these names, which have T and A over there. This T and A is going to play a role in their appearance in the surgery exact sequence. So just take it as a beta by the moment. And there is also some betas which involve the MOUNT-CON assembly map, and now we're going to see it. How do they play? So this is the main theorem. So for P equals 1, 0, or 2, there are maps constructed just putting the Mattei construction over there from the group homology with these coefficients into Rn of these specific parameters there, which fit into the following commutative diagram. So here you have on the left-hand side this beta, which lands on the R group. Then alpha, this is the Novikov assembly map over there. And then the right-hand side is just the Chern-Pontryagin character. And this is the main result. So we use these Mattei maps and fit it into this part of the surgery exact sequence and map it to analysis to the through the assembly map over there. And then this has consequences about the groups R and P. And now you see the consequences. If I have high dimension, this is bigger than 7, at least 7, then if I assume that the rational Novikov assembly map is surjective, then this assembly map is surjective over there. And then, for example, the rank of this R group in this dimension is at least this H0, F0 of gamma, plus H2, F1 of gamma. So this is just by analyzing the specific coefficients which map onto that through this part of the mapping surgery to analysis sequence. And then if this other assembly map is an isomorphism, then the map going from Pn, so this is the positive scalar curvature Bodism, into the real version of the analytic surgery structure set, then this map is surjective. And if you consider this specific n of the form 1 modulo 4, then the rank is at least h1 of gamma with these coefficients. So this is what I wanted to tell you. So thank you.
Thank you very much. Really nice subject. There's questions from the audience. Could you tell Noé us then how you see, for example, H2 gamma with these really weird coefficients in Rn? How are these surfaces there? Oh.
So this is just a group homology with coefficients in real real elements. So they have, before taking classes, so a conjugacy class of a real element is the conjugacy class of an element for which this equality holds over there.
Mm-hmm.
And then this is just group homology with coefficients in the sets of real elements over there.
Oh. But then, well, you have this inequality with the rank of this for this group of with the R group. Well, the R group. So there, this two homology group is not included. Okay, it's just an inequality, no?
It is surjective. So this part of the diagram which I am depicting, so the beta PSC over there in the middle, this is surjective in that case because of the pairing of the two exact sequence, and then I say the rank of R is at least the rank of this, and this is something which only depends on group homology.
Oh. And maybe just a really far, well, it's a little bit different. You know, well, this story of how to prove that there is exotic spheres for dimension 7, and this use the chi genus and the Pendragon classes. You know? So there is a similar story here in this for positive scalar curvature, that maybe there are some exotic structures here.
Yes, I mean, as far as well, there is the alpha invariant, which is the reason why alpha is called here. So this is a KO theoretical invariance for exotic spheres there. So so this is implicit. It's probably not so mainstream, but it's over there, right? So there's lots of constructions, and in fact, these computations you could regard as a measure of the loss of rigidity of a manifold having a positive scalar curvature. So if you see the old papers of the 90s,
Just a minute.
yeah, sure.
About done now.
Okay.
So I found one. Rather seldom I can find a paper in my study because it's such a mess. But a few years ago, I was quite interested in positive scalar curvature and read some nice papers by Mark Walsh and others. And I've got one here that's sort of a survey article by Anand Desai, Dessai, called Torus Actions, Fixed Point Formulas, Elliptic Genera, and Positive Curvature. And so here's what I'm wondering. With positive scalar curvature, at least the A-roof genus vanishes, as you said. what about the classical original elliptic genus, which at one cusp gives you modular forms, but at one cusp, it gives you the A-roof genus, and at the other cusp, it gives you the Hertzsprung signature. So I don't know, if just wondering if there's any reason to see what its behavior is in this setting.
Yeah, but about the Witten genus, I really don't know. So I'm concentrated in this other part of the story. And perhaps another reference for exotic stuff going on is David Wraith. So he also has a paper about exotic.
Sorry, who does?
Wraith, David Wraith. I will write it.
Yeah, maybe you could write in the chat.
So I guess probably David Wraith. So
okay, David Wraith. Okay.
And here, no, we have also a power series like the tangent.
Well, I mean, it's the homological expression of the index over there. So, but yeah, this A-roof genus over there. So this is the beginning. Oh, here.
I will take a look. Thank you.
Thank you.
Is there any other question? So if not, yes, thanks, Noé. Thank you very much for the talk.
Thank you.